Hi everyone. So what I want to talk about today is one of the best theorems in complex analysis, one of the most important and really in some way exhibits the behavior that characterizes analytic functions. It's the Cauchy integral theorem. And the basic theme of the Cauchy integral theorem is that for an analytic function, the behavior of the function on an open set in C simply connected open set really is determined entirely by how that function acts on the boundary of that set. Now, that might not seem shocking or weird, but that's an incredibly strange result, especially if you think about what it says in the land of real functions. So there's no reason to believe, for example, that if you know a function, say, on, let's get a pen up here. There's no reason to believe that if you knew the value of a real function at a and b, so if you knew f of a and you knew f of b, there's no reason to believe that you should know the value of what f does in between those points. I mean, if I tell you, oh, look, I have a dot right here and a dot right here, and so this is a f of a, and this is b f of b, you have absolutely no idea what's happening between those 2 points, right? I mean, f could do lots of things. F could be analytic and do lots of things. There's all kinds of analytic functions that go through those 2 points. Every polynomial is an analytic function, and there's going to be a polynomial of any degree that you want that connects those 2 points together. So in the context of real functions, even real analytic functions in one variable, knowing what's going on the boundary of a region doesn't tell you anything about what the function is doing in the inside of that. And that same restriction applies for real functions in 2 variables as well. It's quite striking, actually, that knowing what a function does on some curve C. So the big idea here is that if I know what f of z does on C, somehow that's going to dictate the behavior of f in the interior. But that's precisely what the behavior that analytic functions exhibit. Now, this is a famous problem in mathematics and physics. We're going to talk about this again later, but the idea of reconstructing a function from the way it acts on the boundary of its domain is called the Dirichlet problem. And the Dirichlet problem broadly is, if I know what f does on the boundary, can I figure out what f does on the inside of its domain? So that is the Cauchy integral theorem. Cauchy proved it when he was very young, I think maybe 21. And the statement of the theorem looks a little strange, but let's just think about exactly what it would imply. So let's let f be analytic inside and across a piecewise smooth closed curve. So analytic inside and across, the way you should think about what that means is that you have some piecewise smooth closed curve. So there's your curve C, and that there's a neighborhood of that set. There's some neighborhood of this that contains the set so that f is analytic on the larger set. So f of z is analytic here. Essentially, we need f to be an analytic function on the curve and not just on the inside of the curve. Okay, so we've got an open set, an open domain. F is analytic on the open domain. The curve is contained inside of it. Then, for any w on the inside, so if we choose a w value in here, we get the quite striking conclusion that I can reconstruct the value of f on the interior, f of w, is equal to the integral around C of f of z over z minus w dz. So you might think to yourself, okay, well, what is that really saying? I have this f of z and an f of w, so you're saying f of w is in terms of f of z. That's not a striking fact at all. But remember this integral only exists on the contour C. We don't actually know what f is doing in the interior. What we're doing is we're reconstructing the behavior of f on the interior by integrating this function around the boundary value. That's pretty weird. This type of object here is called an integral representation. And integral representations are one of the sort of core ideas of contemporary approaches to analysis in engineering. So even the idea of this theorem is important, right? This structure. But the idea is, again, just to reiterate, because this is so important, that this is f on the interior, and it's equal to an integral of f around the boundary. And since that holds for all w on the interior, what we're saying is the behavior of f, the values of f on the interior of that contour are determined entirely by the values of f on the exterior, or rather on the boundary of that domain. Now this kind of seems like a result that might be hard to guess would exist. It's actually hard to see what the intuition behind this is and where the 1 over 2 pi I comes from, what the z minus w itself is doing in the integrand. It's an odd sort of, to me anyway, the first time I learned this theorem, I didn't really understand what this was about. Why we have this divided by z minus w and why that gets us the result that we want. So I want to walk you through an approach to the intuition for this theorem that might help pull the curtain back a little bit about why you might even believe this theorem to be true. And the sort of intuitive walk that we're going to do is going to involve some steps that are not justified. So this is not a proof. It's a suggestion of an approach that you could take to proving this. And Johnston's proof is a little bit different and uses the crash through with the modulus theorem, which is the triangle inequality for integrals. I'll talk about that proof in a separate video. For now, the intuitive approach to this, I think, actually bears a lot of fruit because it shows you how the existence of power series for functions leads to results like this. Why analytic functions consistently show this highly structured behavior, and how it's deeply connected to the idea that analytic functions all have power series that converge on open sets. Okay, so let's begin with exactly what this walkthrough says, right? So what are we doing here? So we're going to suppose that f is analytic on a set containing C in the interior, just like in the picture that we drew before. Okay, so we have some contour C, and we know that we have f is analytic on some set that has C in the interior, so f is analytic like this. So f is analytic so that f is highly structured and nice. And then what we're going to do is we're going to pick a w on the interior, and we're going to make the assumption that f of z can be expanded into a power series about that point w. Now, we don't actually know the Taylor theorem yet, so this is, again, this is just intuition. So when I say that you should find this step iffy, that's because we haven't justified it. So let's just make the assumption that an analytic function at a point can be expanded into a power series that uniquely represents the function. So what we're saying is, okay, if we're going to do a power series centered at w, then we were saying that f of z should be able to be written as c0 plus c1 times z minus w plus c2 times z minus w squared, and so on, right? That there's some power series that represents the function. And normally we write this in sigma notation as n is equal to 0 to infinity of cn z minus w to the n. We're going to just assume that this is convergent on a neighborhood of w, and that we can actually expand that convergent power series out to contain the entire yellow set, which is another theorem we haven't proved yet, but we're just going to assume that we have a nice power series representation that rolls out as far as we need it to go. One observation to make here is that part of the reason why power series are so important is because they recover the values of the functions and all of its derivatives. So f of w is equal to c naught plus c1 times 0 plus c2 times 0 squared and so on. So f of w is c naught. So the value c naught is the value of f at w. So whatever c naught turns out to be, that is the value of the function at w. Okay. So you take this power series, which remember is equal to, you can think about it as being equal to c naught plus the sum from n equals 1 to infinity of cn z minus w to the n. So I could just peel off the first term if I wanted to. And I can divide both sides by z minus w. So I'm trying to lower the order of each term by 1. So if you do that, what you end up with is an equation that has, well, you take this expression and you divide it by w, or z minus w rather, and you're going to get f of z divided by z minus w is equal to c naught over z minus w plus the sum from n equals 1 to infinity of cn. Well, every other term in here, I just drop the power by 1, z minus w to the n minus 1. And I want you to notice that each one of these terms is analytic, right? There's no dividing by z minus w. There's no asymptotes anywhere in here. There's a single asymptote that is on that term, but I've pulled it out of the sum. Okay. Now again, this is a step that all these steps you should think of, these are formal steps, right? We haven't justified why this is possible, but at least algebraically this makes sense to do. Now, if we integrate around if we integrate this, so if we take this expression and we integrate both sides with respect to z around our contour c, what we end up with is the integral around c of f of z over z minus w, that's the left-hand side, is equal to, well, I'm going to do another iffy move here, because really what I'd like to do is I'd like to put an integral right here and an integral right here, and then I want to take the integral and the sums and I want to switch the order. Like when we do a polynomial and I integrate a polynomial and I apply the integral to each term independently, that's the move I want to make here. I want to take this and I want to push the integral inside the sum. So break up the integral into all of its pieces. That step is also currently unjustified, but from an intuitive standpoint, it should make sense that if we have an analytic function which converges uniformly and absolutely everywhere on its domain, then I can switch the order of integration and summation. All right, so after doing that, I end up with the following expression. On the left-hand side, I have this. On the right-hand side, well, I've integrated this term right here, the c naught over z minus w. But remember, c naught is equal to f of w. And so I get c naught over z minus w integrated around c. And then I have the sum of all of these integrals, right? So I've taken this big, long, sort of infinite polynomial, and I've just put the integral on each term independently. Okay? So another way of thinking about this is, what I had was, I have the integral of f of z over z minus w dz integrated around the contour. And then I took the integral and broke it up so that I have f of w over z minus w dz plus the integral of c1 dz plus the integral of c2 z minus w to the first dz plus this is all integrating around c, the integral of c3 over z minus w to the second dz, and so on. So I've taken the integral and I've applied it to each term. Now I've almost got the result that I want. I'm going to make the claim that each one of these terms integrates to nothing. So why do those all integrate to 0? They integrate to 0 because each one of those things is a polynomial and thus an entire function. And I'm integrating a polynomial, so an entire function, a function that's analytic everywhere, around a simple closed curve. And the Cauchy-Goursat theorem says that when you integrate an analytic function on a closed curve inside of its domain, you get 0. So each one of these terms integrates to 0 by the Cauchy-Goursat theorem. And on the other hand, we showed that the integral of 1 over z minus w dz for w inside of a contour, we showed in an earlier example that this was 2 pi I. That if we have a function that has an asymptote inside the contour, and I go all the way around the contour, then I get 2 pi I. I can do that directly with a parametrized integral. Okay? And so that means that this piece right here, well, f of w is a constant with respect to a dz integral. And so what we end up with is the integral around c of f of z over z minus w dz is equal to, well, the f of w comes out of the integral because it's a dz integral. And I have the integral of 1 over z minus w dz, where w is inside the contour, which means that this is f of w times 2 pi I. And if we divide both sides by 2 pi I, we get the result, which is 1 over 2 pi I times the integral around c of f of z over z minus w dz is equal to f of w, which is to say f of w is determined entirely by the behavior of f of z around that contour. Now, don't take this argument as rigorous because it's not. I've suggested some places here where things make sense intuitively, but the justification for these things are some of the major theorems of analysis, like switching the order of summation and integration for an analytic function. That's a theorem. The existence of the Taylor series is a theorem that we'll see in the next section. But from an intuitive standpoint, that's all that's really going on here. We have a power series. We divide by one copy of the power, which puts an asymptote into the expression. And then I just slap integrals on both sides and invoke the Cauchy-Grosset theorem. OK, so now that we've seen the Cauchy integral theorem, let's actually take a look at how we apply it. And so a typical application when you first learn a theorem about integration is to do some basic integrals. And so here's the sort of integral that might come up in practice, right? I mean, it's specially chosen to illustrate how Cauchy integral formula, or the Cauchy integral theorem actually works. So we're doing a contour integral, and it has the form, the integrand has the form f of z over z minus w for f of z equal to the sine of 5z, and for w equal to minus pi over 2. So with those choices, it looks like the integrand that appears in the Cauchy integral theorem, which says that f of w is equal to the integral around c of f of z over z plus w dz, z minus w, w dz. So let's see if we satisfy the rest of the conditions here, which is the function f has to be analytic, and that w value has to sit inside the contour, so it has to be an interior value. So what is the actual contour here? So c is equal to a circle of radius 3. Okay, so this is c, which is modulus of z equal 3. And the w value that it looks like is minus pi over 2, so that's a real number. So if I plot that, minus pi over 2 is about minus 1.7, which means that our value w is about right here. So this is w is equal to minus pi over 2, which is an interior value. So w is equal to minus pi over 2 is inside c. And f of z is equal to the sine of 5z is analytic everywhere. There's no asymptotes. The power series converges everywhere. So sine of 5c is an entire function, which means that the Cauchy integral theorem applies in this situation. So what the Cauchy integral theorem says, by the Cauchy integral theorem, it must be the case that sine of 5 times minus pi over 2, that is f of w, is equal to the integral around 1 over 2 pi I forgot the 1 over 2 pi I here, times the integral of f of z over z plus pi over 2 dz. Those must be equal to each other. And if we want to solve this integral, all I've got to do is evaluate sine at minus pi over 2 and then multiply both sides by 2 pi I. And what you get is minus 2 pi I is equal to the integral around c of the sine of 5z over z plus pi over 2 dz. Because the sine of minus 5 pi over 2 is minus 1. So this is an indirect way of evaluating this integral, but this is one of the ways that the Cauchy integral theorem is applied, is in this sort of manipulation when you have expressions in the bottom that represent asymptotes or singularities. Okay, so let's do another example. For our next example, we have an expression that looks rational, right? I have a z squared plus z and a 2z plus 1, and I might think, I have absolutely no idea how to proceed here. I don't really want to have to parameterize this with an e to the I theta because there's going to be e's and i's and thetas running all over the place, and I'm still not going to get an expression out the other side that's necessarily easy to compute. And is often the case with integrals in complex analysis, sometimes there's tricks you can use. And so the particular trick that I'm going to use for this one to apply the Cauchy integral theorem is I'm going to slightly rearrange the integrand here. So notice that 2z plus 1 over z squared plus z is actually equal to 2z plus 1 over z times z plus 1. And this has two possible places where there are asymptotes. Right, a 0 and a minus 1, and neither one of those necessarily has the Cauchy integral theorem applied to it because the Cauchy integral theorem requires that we have just a single z minus w floating around on the bottom, where w was on the inside of the contour. Well, let's look at the contour. Notice that 0 is inside a circle of radius 1/2, but the point 1, or sorry, minus 1 is outside. So that means if I rearranged this into the expression 2z plus 1 over z plus 1, and then I divided all that by z, this part is analytic. So there's a bad spot out here at minus 1. But that function, this function right here, is perfectly well behaved on a set containing just this, because it has no asymptotes in there. So f of z is equal to 2z plus 1 over z plus 1. What you would say is analytic inside and across the circle of radius 1/2, because it only has one asymptote, and that asymptote is outside. And that means that this integral can be thought of instead as the integral around that circle of the function 2z, well, of f of z over z minus w dz, where f of z is 2z plus 1 over z plus 1, and w is equal to 0. Uh, 2z plus 1 over z plus 1, that's an analytic function, divided by z minus 0 dz. So this integral is the same as that one. That's going to allow us to apply the Cauchy integral formula. So what does the Cauchy integral theorem say? In this case, it says, well, if our z value is 0, then that says that, or our w value, f of 0 is equal to 1 over 2 pi I times the integral around c of f of z over z minus 0 dz, and f of 0 is 1. So you end up with 1 is equal to 1 over 2 pi I times the integral around that circle, c 2z plus 1 over z plus 1 all divided by z minus 0 dz. But then, of course, this is the original integral because all we did was algebraically manipulate it. And so you end up with the conclusion 2 pi I is equal to the integral over c of 2z plus 1 over z times z plus 1 dz. And that was the desired result.